All right, so where we go from here is the discussion on reaction rates. Yay is correct. This week in lab, together we explored the 4 different factors on reaction rates that we're going to discuss in this chapter. So let's think back to the labs that we've done over the last 2 days. Give me a factor that influenced the reaction rates of the labs that we performed.
Surface area.
Surface area. Which lab was that?
We had to crush up the seltzer tablet. I have no idea which lab it was.
And what influence did that then have on our reaction rate?
Smaller surface area, quicker reaction. Well, it like dissolves quicker.
What does powderizing, some kind of thing, do to the total surface area of that amount of substance?
Like of the individual particles or
So the individual particles got smaller, but overall, if you had a,
spreads out more.
yeah, if that tablet was 1 gram, right, that quarter tablet was 1 gram each, and you powderized the one into 1 gram and the other one was just 1 gram a chunk, which one has more surface area? The powder, right? So greater.
But honestly, now I feel like everything
I probably could have moved this all over and fit all of it.
Because I like looked at it and I was not just completely.
All right, what was another one?
Temperature.
Keegan, let somebody else play, right? I mean, come on. Which labs were these? Which examples had temperature as something that we observed, Henry? The tea? How did temperature influence the tea?
The hotter water, the tea steeped faster than the cold water.
Did it even steep at all for the cold water? Yeah, hardly at all. I didn't really see any. So we would say influence then is what?
Temperature. Greater temperature, the faster the reaction.
What was the second one that we did with temperature? Well, that was endo and exothermic. That was endo and exothermic that you're thinking of. What other lab do we do this week that had to do with temperature? We did tablets also, right? You took 2 similar sized chunks of that tablet, one into hot water, one into cold water. What did you observe? Yeah, the hot water went like really, really fast, right? And then the cold water one just sat there and fizzed for probably until you cleaned it out, right? So temperature. What was the third factor that we explored in the lab?
Catalyst.
Catalyst. I'm going to save that one for last, so hang on to catalyst. Surface area, temperature, Grace. Concentration, good. So which lab was this? Which lab was this? What did we do to test concentration? Now, half of you did one and half of you did the other for this lab. Which one?
The acids.
The acids, yes.
Higher potency, faster reaction.
So as you did this lab, for those of you that did the vinegar one, the test tubes that had the higher concentration of vinegar, did they react faster or slower? Faster. Should have just Should have just shortened this to R dot R. So for these three factors, you could see a pattern emerging here, right? Higher concentration, faster reaction. Higher temperature, faster reaction. Greater surface area, faster reaction. And then the last one that we did was the catalyst. This is a little bit more interesting to describe. I'm going to cheat this up here a little bit. How did the catalyst, the addition of a catalyst, influence the reaction that we observed?
Like it sped it up.
Sped it up just by doing what?
Being there.
Being there. Did we have to make the temperature higher?
No.
Did we change the concentration? We didn't do any of that stuff with the catalyst. We just literally added the catalyst to, in the case of our mixture, our hydrogen peroxide. We just add a catalyst, and that makes your reaction progress faster. So why, not till we get done with this. So why does this, all these things, what's really happening, do you think, that's making these reactions go faster? When we change one of these factors, what's really happening? We all observe this, sure, and that's easy enough. Hey, yeah, this is going faster or whatever it is. Those are the observations, right? And that's the important part of chemistry. That's to anchor this concept. But what's really happening? What's going on under the hood? What's that?
I thought you just said what's going on in the hood.
Okay, so changing energy. What do you mean? Okay, good. So the water will have more energy. Those particles will have more energy if their temperature is higher. Yes, they're going faster, right? Greater kinetic energy. Those particles are moving faster in the hot water. But why does that make the reaction go faster? What does that mean? What does increasing the speed of the particles mean when it comes to some kind of reaction? They're more likely to collide. What do you mean by collide? What happens when things collide? Yeah, so for a reaction to happen, right, for two things to have some kind of chemical interaction, right, they first have to be next to each other. And I would say that just being next to each other isn't enough. They have to smash into one another. And so in this case, if that's what we're talking about, why then would temperature influence that kind of thing?
Faster it goes, the more they run into each other.
Where would a car accident, I hate to use this example, maybe I should find something else, but is a car accident going to be more, no, let's not use that word. Is a car accident going to cause more damage in the parking lot here at school or on the interstate? Why? Moving faster, right? There are accidents probably a lot in the parking lot here at school. Most of them are not great, but low speed kind of things, right? And so temperature causes that to be a bigger factor, right? So the faster things are going, the more often they will collide, and that collision may happen in such a way that a reaction occurs, right? Why would concentration matter?
More solid
Sure. Well, why does that matter for a reaction?
because it like lessens the way of no reaction. It has more.
Think about, I agree with you, but think about what's happening. Yeah, so in our parking lot, would there be more chance of a collision between two students if there was 6 cars in the parking lot or 600? 600. right? So concentration matters. Now, if those particles are more likely to run into each other, right, because there's more of them packed into a space, again, that is why you would have a higher reaction rate. What about surface area?
High energy reaction. It has more space to react to.
More space to react to.
Wet. And it's not that wide either, so.
True, but if you put, guys, if you put a chunk of something into the water like we did, and then also powderize that same something and put that into the water, right, guys? So if we do that, right, why does it not all react at once with the small chunk?
Because they're different sizes.
True. Yeah, right? So everything on the inside of that piece of whatever it is protected from some interaction, right? Because it's literally on the inside. You can't get to it. But when you powderize it up, now you have all those little individual pieces that are no longer protected by the size of the chunk of whatever. All right, so last thing is a catalyst. So this kind of doesn't seem to fit the profile of the other things that we've been talking about, right? What's different about a catalyst, do you think? And again, this one is harder to kind of work out in your mind.
Are the chemicals reacting with each other to go for the solid or something?
So the chemicals are reacting with each other, yes. But why does a catalyst who doesn't doesn't participate in the reaction, right? We talked about this. The catalyst is still sitting in those test tubes over there, right? It hasn't changed. So a catalyst helps kind of align the things in that reaction, right? Again, with temperature or concentration, you're just kind of increasing the luck that those things will run into each other in such a way that a reaction happens. A catalyst is kind of like a guide. A catalyst is kind of like something that aligns the pieces, right? So that when they get together, they can react easier, right? Think about a puzzle. If you were going to fit together a puzzle, and you just mix up all the pieces, right? And then you go to put that puzzle together. You have to find each piece, find where it goes, and so on and so forth. What if somebody instead pre-sorted everything for you? Flipped all of them over, put all the edge pieces together, the corner pieces together, right? The similar colors or similar things in similar areas. Would it be faster to do puzzle number 1 or puzzle number 2? Right? Number 2, where all that stuff is kind of done. And a catalyst works in a similar way, that it kind of like will help. Right? It doesn't actually do anything. The same puzzle has to be made, but if things are lined up better, that's kind of what a catalyst allows you to do. And by definition, the catalyst decreases the activation energy Where have we seen activation energy before?
Exothermic, endothermic.
Exothermic and endothermic. Right, so so where on this graph that's just the shape of it. Where on that graph is that activation energy? And again, this might be from your notes from 2 days ago.
Top of the curve.
Yeah, so that's this distance here. So if you decrease that activation energy needed, right, you make this reaction easier to perform at whatever temperature or whatever concentration, right? You just make this easier to go. You make the kickstart of this significantly easier. Lastly, is this endothermic or exothermic as I have drawn here? Exo or endothermic? You're going to have to identify these by the graph.
Endo.
How do you know endothermic?
Because the energy is being put into it.
So if these are the reactants here,
It gets
The product side, right, have more energy. How did they get more energy? Energy must have went into the system. That would be endothermic. Just as a, that doesn't really have to do with this, but since we're drawing this anyway, we might as well have it up there. Questions on reaction rates?